All right, folks, our next presenter is Teagan Leitzke. She is a postdoc at Montana Tech. She is researching in metallurgical and materials engineering department at Montana Tech. Her technical expertise includes aqueous processing, magnetic separation, environmental remediation, and water treatment. Her current and recent research efforts focus on rare earth element separation, critical mineral recovery from slag waste and wastewater, and applications of magnetically susceptible absorptions in water remediation. She's going to talk to us about reimagining contaminant removal, a novel approach to removing and recovering water contaminants utilizing a continuous flow material recovery process. Please welcome Teagan.
All right, thank you. Like Mike said, my name is Teagan, and I am a postdoctoral researcher in Jerry Downey's group at Montana Tech. My talk today will briefly go through our research on a continuous flow material recovery process, starting with a little bit of background and then moving into our adsorbent media, the CFMR technology, and finally where we want the research to go in the future. So first, a little background. Drainage and leaching from anthropogenic sources such as mining can move low levels of contaminants like copper into water systems which can be toxic, especially to aquatic life. Examples of local contamination are the Berkeley Pit, containing roughly 50 billion gallons of contaminated water, and the Northside tailings seen here after rainfall, where we have that blue-green water most likely contaminated by copper. These sites illustrate a need for cleanup and removal of contaminants from aqueous environments, which is where we hope to use our process. So moving onto our adsorbent media, magnetite was chosen because it naturally exists in the environment and also due to its natural magnetic and adsorptive properties. Here we have some SEM images of magnetite. So A and B are both from SkySpring Nanomaterials. A was purchased before 2018 and B was recently purchased in 2021. And then we also have a comparison sample of magnetite purchased from US Research Nanomaterials. So we purchased magnetite from two sources for comparison, where we see the SEM images in A and C show that our particles range from tens to hundreds of microns with a variety of geometries. Also, we see that particles purchased recently from SkySpring Figure B are much smaller and more uniform than the older particles. Using these new particles, we actually found that little to no absorption occurred, but we are still working out, to figure out why the difference in absorption between those two types of particles. So Elisa Hashley, a master's student, has been investigating the effects of magnetite morphology on adsorption of copper ions. She explored magnetite from a couple different sources, first here with magnetite found in chemical storage at Montana Tech, indicated by the CS. So CS 1, 2, and 3 were ground using a high-energy ball mill, where a 49% decrease is observed after 5 minutes, 58% after 10 minutes, and 73% decrease in size after 30 minutes compared to the original. Further, she prepared magnetite by co-precipitation, indicated by the CP. So CP3 was obtained by placing our resultant co-precipitated magnetite chunks into the high-energy ball mill and ran for 30 minutes. So CP3 was not properly ground in the ball mill, but instead formed a thick film on the bottom of the mill canister. Removing the sample resulted in large flakes instead of fine particles as seen in the SEM image. Therefore, CP1 and 2 were ground using a mortar and pestle. So even though we had a 91% decrease in size observed for CP3 at that 30-minute mill time, we did see increased decreases in size for 97% and 98% for the mortar and pestle ground magnetite. So here we have the adsorption information from the CS and CP magnetite. Loading capacity at left and our removal efficiency at right are shown as functions of particle size. The chemical storage magnetite has higher removal efficiencies, greater than 98%, with higher loading compared to the co-precipitated magnetite. Observation of lower removal efficiencies of the CP magnetite indicates complete loading may not have been achieved, leading to that lower loading. Differences between removal efficiency and loading capacity results could be due to altered particle shape and particle size distribution when using the higher energy ball mill or mortar and pestle to decrease our particle size. Both the removal efficiency and loading capacity results do not vary much, indicating a need for a greater particle size difference to look more at the effects on adsorption. So going back to that commercially available magnetite we were talking about earlier, it was also used in adsorption experiments. So these experiments were run using 1 liter of solution containing about 100 milligrams per liter of our contaminant and a dose of 10 or 20 grams of magnetite, mixing at 400 or 600 RPM for 6 hours. So first we have our 20 gram per liter and 400 RPM mixing speed runs. Over 90% removal was achieved in 4 minutes or less for each contaminant, with over 99% removal achieved in 8 minutes for lead and copper. The magnetite concentration was then halved, and mixing speed varied to see their effects and impacts on adsorption. In these cases, magnetite saturation began to occur at 30 minutes, where you see the curves leveling off, with 78% removal at 400 RPM and 79% removal at 600 RPM, with overall removals of 84% in both cases. So clearly, increasing our agitation speed didn't have a significant effect on the kinetics, but the comparable removals display reproducibility of these experiments. So I also had an undergraduate student, Bailey Phillips, work with me on investigating the removal of selenium ions by adsorption on our magnetite. The kinetics experimental results are presented here, where selenium concentrations were about 100 milligrams per liter, and these experiments were run for 3 hours, mixing at 400 RPM. So experiments for both compounds at magnetite doses of 20 grams per liter resulted in magnetite saturation points at around 8 minutes, with removals between 85 and 90% within the first 15 seconds of contact, and overall removals of greater than 95%. Experiments at 10 grams per liter revealed saturation points near 16 minutes, with overall removals greater than 78%. Rapid kinetics of these selected contaminant ions means that our particle residence time and reactor size can be decreased depending on the volume of water being treated. In addition to adsorption, we also looked at cycling. So cycling experiments were conducted to determine the reusability of our magnetite. Each data point was taken after 24 hours of contact using about 2 grams per liter of magnetite. And over several cycles, it is observed that near complete removal of copper is achieved. Final concentrations taken after the final cycle in each case, and noted in the graph legend, were below the detection limit of our instrument, which was 0.1 milligrams per liter. And we observe a linear increase for our interstage strip and regeneration, the triangles, essentially removing all copper in 7 cycles, while an exponential increase is observed using fresh particles, the circles, removing essentially all copper in 3 cycles. So a brief summary of contaminant loading on our magnetite. So I've got examples of copper, lead, phosphate, and selenium here. And copper and selenium have larger ranges in their loading capacities, as the loading experiments were performed with 2 grams per liter and resulted in more complete loading at higher initial contaminant concentrations, whereas the other contaminants were run at much higher doses of magnetite, resulting in excess magnetite and incomplete loading. These results are just the initial stages of exploring contaminant ion capture by adsorption on magnetite. Additionally, looking at the magnetite morphology, further particle characterization using thermogravimetric analysis and the Brunauer, Emmett, and Teller method for surface area measurements will yield more accurate results of particle sizes. And then a larger particle size range will include particles in the actually nanoscale as opposed to just our microscale. And additional synthesis methods may allow for more control of obtaining that larger particle size range that we're looking for to really look at the absorption effect of size and morphology. So moving on to our continuous flow material recovery system, which I'll call the CFMR from now on. I've been working with the 5th generation design, which is more compact and user-friendly compared to older designs. So the CFMR works. You take your contaminated water and your magnetite slurry, and you mix it, and it mixes down until it reaches this guy here. This is our magnetic collection module. So in here is an inline electromagnet. So once our slurry of magnetite and water reach here, our magnetite will hopefully all be captured, and then our treated water will flow out of the system. And once our magnetite is saturated, we can stop the flow to our module, shut off our power supply, and turn our valve to release the loaded magnetite into a separate stream. So we also ran this system in continuous operation to determine how well it performed running for an extended period. Copper solutions were prepared and mixed with magnetite first in this mixing tank here. And then once we had mixed that for a little while, it flowed through our pump system and then up and over and into our magnetic collection module, much the same as the other system. And then our treated water continued past our module, and then just to prevent wasting a bunch of copper solution water, I actually recycled the water, so that's this line coming back into our mixing tank for our 10-hour experiments. And then our electromagnet during these 10-hour experiments was flushed about every 20 minutes. So some results from the continuous operation experiments. This table displays magnetite capture from the electromagnet at the end of each continuous flow or CF experiment. Experiments were conducted using 10 liters of copper solution, agitation speed of 800 RPM, and magnetite doses of 140 grams per liter for CF1 and 2, 200 grams per liter for CF3 and 4, and 170 grams per liter for CF5 and 6. I also want to note that our first electromagnet coil failed during CF3, so I had to rewind a new electromagnetic coil for the last 3 experiments up there. So the high and mid-range magnetite dose experiments at low and high flows respectively resulted in recoveries of about 83% on average, whereas the low-range dose and mid-range flow experiments resulted in low recovery of 38%. Ideally, magnetite recovery would approach 90+%, and potential causes for loss or low recoveries are magnetite loss through the electromagnet, meaning we might need a stronger electromagnet for the flows and doses we were using, or magnetite got caught in the system. If you remember that picture, there was lots of places for magnetite to get caught, and then it could have gotten stuck to the electromagnet itself, because like I said, I hand wound it and then we just like taped it up. So there were some gaps in there where magnetite could have also gotten stuck. So the system and system design are not yet optimized, which also may account for the less than ideal magnetite recovery. Further, for those continuous flow experiments, we were also looking at copper removal over the course of the 10 hours. So initial copper concentrations of 100 milligrams per liter for CF1 and 2, 500 milligrams per liter for CF3 and 4, and 200 milligrams per liter for CF5 and 6 were used. Results for duplicate experiments were averaged, with error bars for % removal representing a standard % error based on slight drift of our continuous calibration verification samples in our ICP OES analysis. So copper removal data displayed in the graph reveals high removal efficiencies for all experiments. As expected, our low initial concentration resulted in the highest removal efficiency of 99%, while the highest initial concentrations achieved a removal of about 80%. Some discrepancies are observed near the beginning of the experiments and are assumed to be caused by non-homogeneous mixing, as some of the copper solution did flow into the pump system before the experiment was started. So we have a little bit of fluctuation in copper concentration in our first several data points. Further, initial absorption occurred very rapidly for our lowest copper concentration, while it takes approximately 3 hours for the higher concentration experiments to achieve over 60% copper removal. These results indicate that increased doses of magnetite may be required to improve our removal efficiencies, especially at those higher concentrations, in order to reduce copper to below the water quality standard of 2.85 micrograms per liter. So moving in a little different direction, rare earths have gotten a great deal of traction recently and are used in a lot of current technologies with applications in magnets, lasers, catalysts, and the medical field. Due to magnetite's success in absorbing low concentrations of other elements, we are working on expanding absorption research to rare earths, especially in low concentration solutions, where to recover these materials, which would otherwise be disposed of as waste. Recovery of these materials from geogenic and anthropogenic sources is crucial to being able to sustain the production of these items that use rare earths. So the selectivity for coexisting REEs and heavy metals absorbing onto magnetite has not been studied in great detail. It's important to study the selectivity, especially when trying to extract precious metals like rare earths from less desired ones in mixed element solutions. Preliminary studies on rare earth absorption have been done by master's student Daniel Galick, and his study consists of 3 types of absorption studies. All of these experiments use 3.5 grams of magnetite in 250 milliliters of solution, with each element having an initial concentration of 100 ppm, and these solutions were all mixed for 1 hour. So his first study, shown here, focused on a broad range of ions relevant to heavy metal contamination or rare earths. The left graph shows competitive absorption of select elements in single and mixed aqueous solutions at different pH levels, and the right presents a comparison of recovery and selectivity coefficients. So these experiments show that chromium was selectively captured by magnetite in the competitive ion solutions and achieved up to 99% removal, depending on the pH, while other elements achieved lower removals, with the next highest at 58% for lanthanum. The second study explored a broad range of rare earth elements. Again, the left graph is competitive absorption, and the right presents the comparison of recovery and selectivity coefficients. Scandium showed selective uptake onto magnetite in mixed element solutions, reaching between 45 and 95% recovery, while the other rare earths averaged only about 1 to 2% removal, depending on solution pH. Also, we note here that higher recoveries were observed at a pH of 5.3 versus 4 in all cases. Daniel's final study focused on potential industrial application for the recovery of rare earth elements from the chloride roasting of rare earth ore. Surrogate solution experiments were aimed at selectively removing rare earth elements from undesired elements, iron and calcium, left over from the roasting process. Again, the left graph is that competitive absorption, and the right is the comparison of recovery and selectivity coefficients. Experimental results indicate selective removal of rare earth elements from the undesired element calcium in this case, and that was possible. While calcium was captured by magnetite at lower concentrations than the rare earth elements, results also suggest that calcium remains captured by magnetite during our stripping process at pHs between 0.8 and 0.9, whereas the rare earths are liberated at those pHs. Further testing and non-surrogate solution experiments are needed to confirm and expand these results. Clearly, we're seeing some promising results for rare earth element absorption experiments, and we look forward to continuing this research. So in addition to rare earths, critical mineral resources are vital. The Energy Act of 2020 defines critical minerals as a non-fuel mineral or mineral material essential to the economic or national security of the U.S. and which has a supply chain vulnerable to disruption. Critical minerals are again used in a variety of applications, including batteries, semiconductors, and electronics. Recovery of these materials, again, from those geogenic and anthropogenic sources is crucial to being able to sustain production of products that use critical minerals. So in addition to mixed and single contaminant surrogate solutions, I treated water from the Clark Fork River to assess magnetite's effectiveness as an adsorbent on real water samples. Multi-stage with 4 stages, MS, and single-stage, SS, adsorption experiments were performed on these CFR samples. Each stage lasted an hour, with samples being filtered and acidified immediately after each stage for analysis. And samples with a U are the untreated samples. Water quality standards were obtained from DEQ7, the EPA, and WHO guidelines, where dashes indicate I could not find a value for them. So how does this tie into critical minerals? Well, 5 of the analyzed elements shown here are classified as critical minerals. So we have zinc, arsenic, antimony, gallium, and rubidium. In these cases, the final stage resulted in concentrations under aquatic life standards. Though zinc and arsenic had initial values already below the standards, magnetite was able to further reduce their concentrations. For antimony, it is observed that only 1 stage is required to remove contaminants below the standards and to reduce gallium to below the detection level of the instrument. Rubidium slightly decreased in concentration after MS1 and SS1 experiments and remained at that concentration for the MS experiments. These results, again, are promising for using magnetite as an adsorbent to remove a variety of contaminants, especially critical minerals and REEs, from affected waters. So what does this all mean? Progress is moving forward, but we're still collecting data needed to develop statistical models for optimization and improving system design to accommodate different types of applications and contaminant feeds. Overall, results from this research reveal that the CFMR process may be a promising solution to water pollution. Additionally, the process can be modified for a variety of applications, including environmental remediation, the prevention or minimization of contaminant release from industrial and municipal wastewaters, and recovery of valuable materials from waste or recycled materials. We're also looking to expand the CFMR system beyond copper removal and recovery to real-world systems involving highly valuable materials that need to be recovered. We especially want to explore rare earths and critical minerals. Further, real-world systems with varying feed solutions, we want to explore the implementation and optimization of the CFMR system in those real-world systems. So I want to be able to do a lot of this work without a lot of these folks, especially my advisor, Jerry Downey, and funding from NSF EBSCOR. So thank you. Any questions?
Any questions for Teagan? I'm sorry, I didn't.
Teagan, I'm wondering how long the magnetite holds on to the elements that comes out if you wanted to take the rare earths or the other critical minerals and use them for something else, since you're not just storing them.
Sure, yeah, we can, it's actually element dependent on how the strip and regeneration process works, but Daniel's work, looks like he was stripping the rare earths off at very low pHs between that 0.8 and 0.9. So I haven't done leaching tests necessarily, just sticking the magnetite in a solution, but we're using a stripping and regen process because we know there's materials on there that we want to get off and reuse. So.
Any other questions for Teagan? One more.
Have you considered adding that or doing a small-scale project up at Zortman, Landusky, to see if that might help.
I have not, no.
You should talk to Wayne.
Okay. Thank you for the suggestion. Appreciate it.
All right, not seeing other hands up. Thank you, Teagan.